Hey, welcome everyone. I'm Paul Deppenbaugh. I'm the editorial director at Metal Architecture Magazine. We're glad you've joined us for today's webinar. Today we're presenting a webinar, Metal Composite Material Building Code Fire Requirements, and it's presented by ALPOLIC. This is part of our Metal Architecture webinar series. Our presenter today is Jim Moses, and I'm going to turn things over to him in just a moment. First, let's do a couple of little house cleaning things. Jim is going to take questions, but we're going to hold them till the end of the webinar. While we're going through this, I encourage you to submit it on the screen when you think of it. I know some people are reluctant to post questions because they may not want the whole audience to see them, but in this app that we're using today, I'm the only one who can see the questions, so ask away. And for those of you who are interested in AIA credits or certificates, that's going to be handled automatically. Please allow us 7 business days for everything to process. Tomorrow you're going to receive an email exactly 24 hours after the end of this webinar that have links to more information, including how to get answers on specific questions and a follow-up. So look for that tomorrow afternoon. But now let me turn things over to Jim. Jim Moses is the Technical Services Manager for ALPOLIC Division of Mitsubishi Chemical America, a leading manufacturer of ACM, MCM products. Prior to joining ALPOLIC, Jim worked with several companies, including GTE, Tyco International, and One Steel Australia. He's a registered professional engineer with an architectural engineering degree from Kansas State University. And Jim's got more than 40 years of experience in the commercial, industrial, and international building industry, much of it directly involved with standards and code development. So Jim is just an excellent person to have on this. He's expert. You're going to want to ask a lot of questions. Jim, take it away.
Okay, Paul, is my screen up?
Your screen is up and we can hear you.
All right, great. Good afternoon, everyone. I'm Jim Moses, and I'm with Mitsubishi ALPOLIC. And today we're going to talk about metal composite materials and building code requirements. That's basically the material and what the building code requires from a fire point of view. All right, best practices. We're an AIA provider, so those will be handled here. This is copyrighted. This is all good stuff. My marketing people make me say it. So we work pretty hard on this stuff. Okay, today, what we want to talk about is explore some definitions of non-combustibility. Interestingly enough, combustible is not proven, but non-combustibility can be. We recognize the base elements of an exterior wall assembly, those things which make metal composite material and the impact on the design of exterior walls. We're going to review the IBC requirements for NCM cladding. Those have changed somewhat over the last edition or so. We're going to try to understand the applicable fire testing per the IBC for exterior wall assemblies. We're going to focus pretty hard on the NFPA 285, which is the bedrock test. And then we're going to discuss a little bit the role of engineering judgments and letters of equivalency for those systems which have not been tested. Introduction, the MCM, metal composite materials, a very versatile cladding material. It gives designers a lot of choices, a lot of colors, a lot of flexibility. It sometimes takes a little bit of a bad rap here lately, but it is a very, very versatile, worthwhile material. And when you use it in accordance with the code, it's both versatile and safe for all of your projects. Let's talk about combustibility a little bit. Everyone believes they understand what the term combustible means, but quite frankly, the definition of combustible changes from country to country to country. It's somewhat of a political term, if you will. Most countries define what is non-combustible, and that is a matter of setting what conditions under which a particular material will not flame. Okay, All material eventually can burn, but what conditions are acceptable for it not to burn under? Not all of the countries agree. In fact, it is different for the US than it is in Japan, which it is in the European Union. Even Canada has a somewhat different definition than the US does. So it's not a universal term. And if you take nothing away from this other than that, combustibility is not universal. It is not a scientific, well-defined term. It is basically a code term determined by the countries that basically are using the products. In the US and Canada, combustibility is all about three items. It's about flaming, it's about mass loss, and it's about temperature rise. The US and Canada set limits on these criteria, and if you meet these limits, then you can be classified as non-combustible. While both US and Canada use the same three criteria, they don't measure them exactly the same. In the US, the IBC code test for combustibility is ASTM E136, and it considers a material non-combustible if it has less than a 50% mass loss, a temperature increase of less than 54 degrees Fahrenheit, with no flaming beyond the first 30 seconds. And this is all set in an oven that is set to a 750 degrees C temperature. So those three things will determine whether or not a material is considered combustible in the US. In Canada, the S114 uses the same three criteria and actually the same test apparatus, but their limits are a material is non-combustible if it has less than 20% mass loss, a temperature increase of less than 36 degrees C, with no flaming beyond the first 30 seconds. So as you can see, a material can actually be considered non-combustible in the US and combustible in Canada, or even vice versa. Let's talk about middle composite material for a minute. They are basically a composite material that's produced by the continuous bonding of two thin skins, middle skins, under heat, pressure, and tension to either side of a thermoplastic core. The middle skins are typically aluminum, although they can be stainless, they can be copper, they can be zinc, they can be even titanium. The thermoplastic core allows for uniform expansion contraction, and it assures thermal stability, no oil canning, that type of thing, and evens out the product performance. So the core is a very important part of a composite. You basically have, again, the different metal skins: stainless, titanium, copper, aluminum, zinc. It's very rigid, it's very flat. It has an excellent strength to weight ratio, therefore deflections are easily manageable. It's pre-finished, therefore it's coil coated, which gives you a finish that is second to none. And it's used as material for exterior and interior applications, primarily walls, but canopies, column cladding, fixturing, all types of things, because of its lightweight and its flexibility. This is what MCM typically looks like. Primarily it's painted, which is typically aluminum. So you'll have a core with aluminum skin on each side. There'll be a surface treatment on the finish side, which then has a primer, a color coat, and perhaps a clear coat, not always. The backside will have basically a surface treatment and a primer. The natural metals, which are stainless, zinc, copper, titanium, are basically a core with that natural metal then bonded to each side. There is no finish on those natural metals. If it's copper, it's a plain copper. If it's zinc, it's pretty much a plain zinc, etc. The cores are an important part of the composite. They're what allow a composite to be much lighter than, let's say, a solid aluminum plate. There are basically two types of cores in the MCM world. There is a polyethylene core and a fire-resistant mineral fill core, which we typically call PE for polyester and FR for the mineral fill. Polyester is something that's used by code under 30 foot or under 40 foot from grade, excuse me. And FR is something that's required 40 foot and above per US code. Both of these cores are regulated by the IBC. Both of them can be used in the proper circumstances under the IBC. And they're both rated Class A under ASTM E84, and then the Canadian version, which is S102. And we'll talk about these tests a little bit more further down in the presentation. But there's two cores, the fire-resistant core and the polyethylene core. Now, the NCM by itself can't be used as an exterior wall all by itself, I guess is what I'm trying to say. It has to be worked into a cladding system. These cladding systems are literally hundreds of different specific cladding systems, but they all pretty much fall into one of two general categories. You have sealed systems, which are what is traditional, joints will be caught or are sealed with a dry seal. Moisture and air is kept on the outside of the panel. And you have rain screen systems where some amount of moisture, some amount of air is allowed to penetrate through the system into the interior of the wall. When you looked at sealed systems, there are really two types. The most common is a wet seal. I think I did. Sorry about that. The most common is a wet seal system. Okay, the wet seal system basically has a joint that is sealed with caulk. It's probably the most economical and the simplest way to seal the joint in a cladding system. And most cladding systems with a wet seal will look similar to what the picture is here. The other type of sealed system is a dry seal. It's virtually the same kind of system, but rather than a wet caulk put into the joint, there's some type of gasketing. This shows a solid plug gasket, which there's a couple of systems, a number of systems out there that use. They also may use gasketing, rigid silicone gasketing in the joint itself around the edges of the extrusion. But both of these systems typically are intended to keep water and air on the outside of the cladding system. Wet seal tends to be less expensive than dry seal. Dry seal tends to be probably the most expensive of the cladding type systems. Then you have rain screens, and there's really two types of rain screens as well. There's the pressure equalized rain screen. Now with the pressure equalized rain screen, some amount of water, some amount of air is allowed to penetrate through the joint, and your actual building envelope will be the air-water barrier, which is typically back on the face of the substrate. Now, a pressure equalized system is a very specific kind of system. There's a very specific standard and test, which is the ALMA 508 test. It's a pass-fail test. And basically, it measures how much air, how much water can penetrate the surface. It measures how fast the air cavity will equalize with the outside atmosphere. And it makes sure that water can get back out. It also talks about how wet the substrate can be. So this is a very specific, gives the designer very definite criteria to design to, okay? Quite frankly, I'm a big advocate of the ALMA 508 pressure equalized rain screen systems. The other type of rain screen system is called a drain back ventilated. Now this is similar, except there is no pass-fail criteria for a drain back ventilated system. There is a standard, but it's a rating standard. So what this standard does is it basically rates how much air, how much water passes through the face of the system. It doesn't tell you about wetting. It doesn't tell you about drainage. It basically leaves it up to you, the designer, to make sure that your air-water barrier and your interior wall system can handle both the air and the water load. It's probably one of the simpler ones out there, but it puts a little bit more onus on the designer to make sure that his system is adequate to handle both the air and the water load through the cladding system. Now, when you look at a cladding system, you're looking at everything, as I would call it, from air to air, outside air to inside air. So that's all the components of the wall. So typically people think of the MCM because it's the face of the wall. Let's call it the lead singer in the band, if you will. But there are a number of products in the wall that will determine whether or not the assembly is combustible or not. You have to look at the insulation, you have to look at air water barrier, the substrate, all of those things between outside air and inside air have to be taken into account to ensure a wall that performs in a fire manner as you expect it to. Now that brings up the question of energy efficiency versus fire performance. Okay, continuous insulation is pretty much the standard these days, and it works very well from an energy efficiency point of view. Unfortunately, many of the very energy efficient foam type insulations, which have very high R values, okay, are also relatively highly flammable. So you go back to a tried and true, something like a mineral wool, which is very less flammable, but it takes a whole lot more mineral wool to get the same insulated values. So it's very important that when you look at this exterior wall assembly, that any insulation that is used in that wall should have been tested per NFPA 285 as well. Maybe in the same test with the cladding, that's not unusual. Maybe in a separate test, but it is the whole wall. It does you no good to put, let's say, a fire-resistant MCM on the face of the wall and then fill the cavity with a very flammable insulation. That is a recipe for disaster. So all of the parts of the wall, through the depth of the wall, need to be checked for their fire characteristics, and they should all be tested per an NFPA 285 test. And we'll talk about that test in a minute. Okay, I gotta say here, the second thing to take away from this is that in the US, our building codes are second to none. No construction is without risk, but the building code, if followed, will minimize that risk dramatically. The building code is a living document. The IBC is updated every 3 years. New things get put into it all the time. And because of that, we have the safest construction environment, I believe, in the world. We have not had many of the issues that other places have had because of our building codes and the adherence to them, and quite frankly, the enforcement of them in most jurisdictions throughout the US. So one of the big things here is follow the building code. There's a reason it's written the way that it is. So let's talk about the code specifically as it relates to MCM and then fire. In the US, there is a very specific section that deals with composite materials, and it's been there since pretty much the first IBC in 2000. Currently, it is section 1406. However, if you look at 2018 and before, it was 1407. Same section, same wording. Don't know why they changed the number, but they did. But it is currently IBC section 1406. However, that is a model code. So you need to make sure that your local code has adopted the IBC, or if they have not, which there are a few jurisdictions out there that haven't, what does the model code itself say? Or the local code itself say compared to the model? And if they have adopted the model code, which version have they adopted? It is not unusual for me to see, let's say, 2012 IBC to be the actual code of a particular county, city, or even state. In the code, there are a number of tests, specific fire tests, and that's what we're talking about today. Probably the most important is ASTM E136. It's found up in section 703.5. It is a test to determine non-combustibility. If you do not pass this test, you are considered to be combustible, and all of the rules for combustible materials apply. The Canadian equivalent to E136 is S114. We talked about that a little bit earlier. The other test, which most all of us, especially old folk like myself, are familiar with, is ASTM E84. It's found in the MCM section as well. It has limits. E84 is a surface burning test. It establishes a flame spread up the surface and a smoke development index. It's a material test. So basically, if the flame index is less than 25, smoke is less than 450, you have what's considered a Class A material. Okay. In the MCM world, typically both PE core and FR core will meet ASTM E84 limits. In the 2018 and earlier code, there are some alternates which call out self-ignition temperatures. Okay, that is ASTM D1929, which will determine what self-ignition temperatures are. For most MCMs, even the PEs, they are well up into 600-700 degrees Fahrenheit. So it's not low, but quite frankly, in the 2021 code, this is eliminated because the alternate conditions were eliminated. And this is a good point to just say that the biggest difference in the current code versus previous codes is before there were certain alternate conditions under which you could take MCM material all the way up to 75 feet without an NFPA 285 test. Those have been eliminated. Right now, the only criteria is 40 foot and less. 40 foot and less from grade, PE material is acceptable. So if you look at 1-story, 2-story buildings, PE material works very well. If you get above that, material that has passed the NFPA 285 must be used. And in Canada, those equivalents again are the S114 and the S102. Now we're going to hit the 285 a little bit hard. The 285 basically is a test for combustible material in non-combustible construction. So it's a well-recognized test. It's been around since the late 80s in one version or another. And the whole concept of the 285 is you have a building fire, which has shattered the window. It has reached out looking for extra oxygen, and it has basically climbed the outside of the building, or is trying to climb the outside of the building. Okay, that's the scenario that the 285 was designed to mimic. The first NFPA edition was in 1998, although before that, this was a section in the UBC, the predecessor to the IBC code back into the 80s. And the point about this is 285 is a living document. It isn't something somebody thought up and got chiseled into stone. There have been a number of different versions. The latest was 2019. That's only going to be true for another month or two. There will be a 2022 edition, which has been approved and is just purely waiting publication. And we'll talk about some of the differences in these later editions of the 285. The test is pretty straightforward. It's done in a concrete test apparatus, which is basically got the ungainly name of the intermediate scale multi-story apparatus. Consists of a room, concrete, a second floor, another room above, and then the face is where the test wall is rolled up against. So you basically make the fourth side of the room with the test assembly. That's the wall you are testing. You look at this from the front. It is instrumentated with a large number of thermocouples. Basically, they go up the center, they go across the top, 10 foot above the top of the window, and this doesn't really show up. They also come down both sides. So basically, you have this window in the middle, a fire starts in the room below. 5 minutes later, they start another fire at a burner right at the bottom of the top jamb of the window. And then every 5 minutes thereafter, they increase the heat up until 30 minutes, it's all shut down, and you determine, well, by then you know whether you passed or not, but you determine what the end is. So the procedure is you start recording, you record your ambient conditions, you turn the in-room burner on for 5 minutes, you ignite the window burner, then 5 minutes later, you increase the energy at 5-minute intervals. At 30 minutes, the burners are turned off. At 10 minutes, you watch it on the wall, and then you take it all down, look at the back of the panel and the front of the sheathing. This is an in-progress test. This test does meet the requirements of the 2019, which very specifically required a vertical joint up the center and a horizontal joint basically 1 to 3 feet above the window. That was the major difference in the 2019. Passing, there's a lot of things that have to happen to pass this test. The most important and the most common failure point is that at that thermocouple 10 foot above the top of the window, the temperature shall not exceed 1,000 degrees. And there's actually 3 thermocouples in the depth of the wall. And the one that almost always fails, if it's going to fail, is the one at the outside surface of the wall. You also can't have flame, which actually propagates beyond the flame plume. In other words, the gas has a flame plume, but the material itself can't burn past that flame plume. The flame also can't go sideways out either side. You can't rise more than 500 degrees in the second floor. You can't have any flames in the second floor, and you can't have any flames beyond the intersection of the test sample and the test apparatus. In other words, they can't be spurting out the sides or the top. Again, the most common one that if you fail or is going to fail is the 1,000 degrees at thermocouple number 11, which is right in the middle of the wall. Okay, that's another look. We'll be looking at this a couple different times, different ways. It's important enough to make sure that there's a fair understanding. This is a successful test, by the way. No one ever claimed that at the end of 30 minutes of a very intense fire, you're not going to have damage. You do. One thing about this particular picture I like to point out is you see this buckling here of the top skin. The fire retardant, the mineral that's used in the core is actually a fire retardant. It actually turns into steam and aluminum oxide at about 400 degrees. So in doing that, it actually buckles the skin a little bit. but it also cools the fire. This is the same wall that's been taken down. As you see, we lost the front panels down here. As you look back here, this particular wall didn't have insulation in it. That was considered a worst case at that time. And you can see we burned a little bit of the air water barrier, but nothing but a little bit of char. This is another look at the test buck itself, 14-foot wide, 18-foot tall. The window in the middle is a 5-foot wide window. The burners are inside the bottom room. They're a window burner at the window, and every 5 minutes it gets hotter and hotter. We'll run through this just a little bit quicker. Here's a picture of it before. Here's a picture of it during. This is the Canadian test. It's somewhat similar, but it's a bigger test buck, and there's slightly different criteria. It's actually a hotter test, but the same kind of thing happens. I always like this picture because this black smoke, this was actually done on a wood framed wall. It did not pass. All right, there are hundreds of different types of configurations for an exterior wall, an NCM wall. This is a very expensive test. It's a very time-consuming test, so not all of them can actually be tested. So engineering judgments, letter of equivalencies, are very important to the wall industry, and they're basically where a responsible engineering firm, a fire engineering firm, will look at a wall system, look at the available testing, and basically say, yes, this wall, if tested, would have passed the NFPA 285. And this is a good place to say that the major difference in the 2022 NFPA 285, which is coming out as we speak almost, is that there's been an appendix that has kind of laid an outline for how engineering companies should do their letters of equivalency, how those engineering judgments should be done, so that there's some uniformity across the country and across the engineering profession as to how those are done. That is the major addition to the newest edition of NFPA 285. The things to look about and the things that they look at from a engineering point of view, some of the parameters are, what is the cavity depth? General belief is deeper the cavity, the more the issue. What types of insulation? As I've said before, some insulations are more or less very limited flammable, some are extremely flammable. That type of insulation makes a difference. Types of weather-resistant barrier. The air-water barrier may be flammable, may not be flammable. Again, that's something that needs to be looked at in an engineering judgment. What is the type of sheathing? Is it dense glass? Is it exterior gypboard? Is it something as a plywood, for example? That makes a difference in this test as well. And then you look at the mounting extrusions. They're not as critical as most, but that's something to be looked at. If in fact you pass the NFPA 285, that wall can be used in all 5 types of construction in the US that's governed by the IBC. All right. PE material can be used in all types as long as it's kept under 40 foot from grade. Used to need a 5-foot separation, fire separation, but that's not in the current edition of the code. And any building construction type over 40 foot must have a wall that's compliant with NFPA 285, and the FR core material is the best way to ensure that compliance. This is a cross-section of the typical types of walls you're going to see in the test. This is one where you have the cladding on the outside, an airspace, a continuous insulation, if you will, a combustible material, which is a air water barrier setter, and then a sheathing. You can see by the dots the exterior thermocouple. There's a thermocouple in the cavity, and there's a thermocouple back in the wall. Interestingly enough, a lot of people assume that the thermocouple that's in the air cavity is the one that will get the hottest, and that typically is not the case. It's typically the one that's sitting about a ½ inch off the front of the wall. This is the case where you have an air cavity and now a non-combustible or limited combustible insulation in place of a substrate. They put an extra thermocouple actually in the insulation itself. So there's 4 thermocouples. Again, typically failure will come to the outside thermocouple. Specifications, you need to know, are you above 40 foot from grade? If you are, you need an NFPA 285 test. That's the most important thing in a specification. The other thing is ICCS reports. If there's an ICCS report that has required the NFPA 285, that's another good way to ensure that the material is in compliance. Yeah, in conclusion, fire events, unfortunately, have been a fact of life throughout history. And recently, we've had some pretty bad ones in basically various countries around the world. We have not had those type of events here. And I truly believe it's because of the US-Canadian code have been extremely attentive to the dangers of both building construction in general and fire code. So the provisions are comprehensive. They're a little bit confusing maybe, but if you step through them, you will end up with a construction that will be safe and pleasant to be in. Wall cladding featuring MCM over 40 foot must have a fire resistant core and must be fabricated in an assembly that can pass NFPA 285. There just is not any other code compliant way of doing it, and quite frankly, that's the way it ought to be constructed. I want to thank you for your time. I thank you for sitting through all of this. Hopefully some of you are still awake. And I guess at this point, obviously, I do work for ALPOLIC. We have a lot of documents about fire on our website. And at this point, you know, the presentation on my part is pretty much over.
Thank you, Jim. That was great. We do have a number of questions here, if you're game to answer some.
Always game for questions.
So you did talk a little bit about, or you did talk about the kind of the above 40 feet, you need to have an FR core, is there kind of a decision-making matrix that determines if a project needs to meet NFPA 285, or is it just that 40 foot?
That 40 foot, yes, that 40 foot is the primary, and I believe, I'm thinking through it, pretty much the only requirement for, at least for MCM, is the only requirement that says below PE core is acceptable, above FR core is required. And I want to say this properly because the code itself never calls out FR core. It calls out the NFPA 285. And certainly in your typical MCM material, the only MCM material that will meet that NFPA 285 is the FR core. So yeah, 40 foot's it. That's the criteria.
All right. So somebody else, you have to have FR core 40 feet from grade, but on a single project, can you mix FR core above 40 feet and the PE under 40 feet?
The answer to that is that's been very specifically been asked of the IBC, and they say yes. But I'm going to throw a word of caution here. All right, from the outside, you cannot tell the difference between FR core and PE core. They look exactly the same. So if you try to mix the two on the job, there is no way to show that PE didn't accidentally get put above 40 foot. Or if I have a building inspector that says Well, you've got to prove to me that that panel right there is an FR core panel. There's no way to do it without taking it off the wall. So we highly recommend to not mix the two together. There's just too much possibility for error. But technically, per the code, yes, you can.
Is there a rule of thumb on what kind of system to choose, whether you use a sealed, wet, pressure balanced rain screen, which I think was the one you said you kind of was your preference? The rule of thumb, does that apply to, like, say, a desert location versus a moist environment, or a height limit on the buildings, how tall buildings versus two-story building? Are there rules of thumb for selecting those kinds of?
Yeah, there's always some kind of rules of thumb, but reality is, if these systems are done correctly, you can do a rain screen in a wet environment versus a dry environment. You can do a sealed system, wet, dry, hot, cold. The truth of the matter is the market pretty much drives what's being used. At this minute, and these numbers are not exact, but they're in some ballpark that works. I would say of all of the commercial cladding that's going up right now, probably 75% of it is a rain screen of one type or another. Probably 20% of it is a wet seal system, and the rest is typically dry seal, et cetera. It's kind of how the market moves. Rain screens are very economical, but they're not. They don't have some of the problems of putting caulks in joints. I always thought it was interesting. You have a 20-year finish, you put a 5 to 10-year caulk in the joint. That's a little bit of a misnomer. But no, it really is. It's what your fabricator is going to bid you. They all used to be dry sealed, then they all were wet sealed. Now they're primarily rain screens. You do have some choice between a pressure equalized and a ventilated drain back. I would always opt, my personal opinion is for pressure equalized, although you're going to find many people will be able to provide drain back, a ventilated drain back, somewhat a little more economical.
Is there any difference in the fire performance among those systems? Is one better performer on the NFPA 285 test than another?
I have to chuckle because this is where the industry and some of the fire consultants disagree. But I think you're going to find in the new code that comes out, they are going to say from a fire performance point of view that the rain screen is a slightly worse case, if you will, than a sealed system. So what you will find is most of the manufacturers, certainly from this point on, will be doing their test with rain screen systems. I personally have probably sat through a dozen of these tests, both rain screen and wet seal and dry seal, and really haven't seen any performance difference between them. But the concept of the joint being able to breathe a little bit leads to the thought that perhaps there's more air, more fresh air in the airspace. We haven't seen that effect, but I couldn't ignore it.
I would mention to the audience, if you haven't seen an NFPA 285 test, I think there are videos on YouTube and elsewhere, including using, I think, MCM assemblies. It's pretty fascinating process to watch live.
Absolutely, I would agree with that.
Yeah. I've got a bunch of questions here, so I'm just going to keep going. I don't think I asked this one already. Are there any height or story limits for MCM using MCM panels? I think they're on some of the tallest buildings in the world, aren't they?
Yes, they are. And once you get past the 40-foot and once you get into the NFPA 285 compliant, the answer is, from a national point of view, no. I don't know of any local codes that put a height limit on it, although I will be honest, occasionally one of the big cities talks about changing things one way or another. But at this minute, I'm not aware of any other height limits other than the 40 foot.
That's a great segue because somebody is asking about the New York City Building Code, which is, I think is up, changing again this year, whether there are any changes regarding MCM materials. Do you have any insight on that?
The only thing I'll say that is if you understand what the New York City Building Code is doing for exterior walls, you're doing better than I am. My understanding is right now is that they have actually put out a lot of you shalls and then are at the moment doing some reinterpretations of what you shall means. So it is, in my opinion, right now very unclear. I'm a member of a couple of different groups which are trying to figure out what they want to do. But in essence, what the New York City Code is trying is they're trying to establish fire blocks interior of the wall on some type of regular basis. That's my understanding. But as to specifics, I don't think anyone knows what the specifics actually are at this point.
You talked way at the beginning about combustibility standards and the E136 test and the S114 test for the US and for Canada. Are there variations in the combustibility standards for, say, the EU and Japan compared to those two tests?
Oh, absolutely. The EU has gone to a small calorimeter type testing and to a series of gradations called A1, the least combustible, A2, down the road a little bit, B1, B2, C2, C1, C2. I think it even goes up to an H1, H2. These are all based on pretty much small scale tests and a matter of total heat output, total heat content of a material. They are not compatible to the US E136. In other words, I don't know. We have personally looked at various A1, A2 material. A2 may or may not meet 285. I know of a few that have been tested that don't. A1 may or may not meet A2 E136 as well, or perhaps a 285. Australia is another good example. We're an international company. We actually market a material in Australia, which by their code is considered non-combustible. However, it will not meet E136 in the US either. So in the US, so it's non-combustible in Australia, it's definitely combustible in the US. Even the FR designation, the more common FR, at one point was considered non-combustible in Japan. So these are all separate. And this is something that confuses people, especially in the era of the internet. Okay, what works in Europe and what they consider, the best stuff isn't in the same scale as what we're talking about in the US or what's being talked about in Australia, or Japan or anywhere else. I can't emphasize that enough. Just because you've heard somebody say this is non-combustible, they're using it in Sydney, okay, will not help you a bit if you use it here and try to call it non-combustible.
I got another question here, Jim, from somebody who's, and we may be straying over into proprietary issues, but they have seen a product offering called an HD MCM to differentiate it from the PE and the FR. Can you clarify that at all? I'm not familiar with HD MCM.
HD? Well, I can only talk about ALPOLIC. HD, we have an HD product. It has nothing to do with the core. It has a slightly heavier skin.
All right. So an HD product could have a PE and or an
yes.
FR.
Yeah.
Okay. All right. And it's just a thicker metal?
Right. It's your typical MCM skin is 0.5 millimeter, 020. The HD skin is 032. A little bit thicker.
There was another question. I've got a couple here, and I'm trying to jump around, and I may have lost my. Uh, let's see. We talked about combustibility. Oh, I know what I wanted to ask. Somebody had. So I think we need a little more clarification about who does these assembly tests, the NFPA 285, and because the person is asking who pays for it in NFPA 285. Is it the contractor? And that leads to the question, how do these engineering equivalency letters work as well?
Okay, all right. The NFPA 285 is a fairly expensive test. And I can tell you the evolution has been originally, many of these tests were done and paid for by people like ourselves. People in the MCM world, we wanted to show that it was a safe material, so we do those type of tests. Now, most of us that make composite material don't make a system as well. We don't do the aluminum and the cladding systems. So obviously, those tests that we did were done on a number of different systems out there, which gives a fair idea of what types of things are important to the test as far as aluminum and systems goes and what's not, because they're done over a number of them. Quite frankly, in the last 5 years or so, many of these tests have been done by the insulation guys. Basically, I have a new polyiso insulation. I want to show that it will work. We go do a test, and I want to test it since they're going to be using it under MCM. I want to test it under MCM. That's a fairly common thing as well. Rarely do these tests get done on a specific project basis, primarily because of cost, and it takes a little while. The test itself takes about a week to set up and run, but it takes a number of weeks to fabricate the material and that type of thing. So typically what you're going to find is these tests are done by system fabricators, either the MCM sheet fabricator or manufacturers such as ourselves, or the system fabricator, of which there are literally hundreds and hundreds. Some of them are very large companies. Now, what happens with an engineering judgment, because far more jobs are done on engineering judgments than done on actual tests. If I wanted to pull a number out of the air, I would say probably less than 10%, certainly less than 10% of the cladding systems out there have ever actually been tested in a 285. So what the major fire consultants will do when they do an engineering judgment is they will look at the components of the wall that they're evaluating, and then they'll go to manufacturers like ourselves, the other people in the industry, the test labs, and they will ask for example, under a non-disclosure, we provide many of our test results to, let's say, a fire consultant engineer to see what those tests were, how they happened, and how they compared to the system that they're evaluating. And then basically they go and do their engineering judgment on which things are important and which things aren't. A lot of that has been a little vague in the past, but it's going to be much clearer with this new edition of NFPA 285. The engineering judgment section is in an appendix, so it's not the weight of the standard, but it's very clear about which parameters they believe are important to an engineering judgment and how they should be looked at. That probably wasn't the world's best answer, but I don't know that I got a better one.
It's a complicated question. This one I think is fairly simple, and somebody's asking whether using Tyvek in an assembly would comply with NFPA 285. Maybe the better way to ask that is using Tyvek would cause an assembly to fail 285.
Well, and the right way to answer that is using a building wrap of any kind should be asked whether or not that building wrap has been tested in an NFPA 285 test. Because there are a number of building wraps that have been. Some have passed, some have not. So, I won't get into a particular brand name, but, let's put it this way. Companies are usually not shy if they've passed the 285. That's usually something they're pretty proud of. So to ask whether or not a material has been tested in an NFPA 285 test certainly is not insulting to anybody who's actually done it.
That's a lot of great questions, and I appreciate everybody for asking them. I'm going to encourage you to, if you have specific questions, to follow up with Jim about them. I suspect that Jim would love to answer them for you. But I want to thank him for a great presentation today. If anybody also wants some more information, you can see it here on the screen there. You can go to alpolic-americas.com to get more information on that. A little reminder about the AIA credits and the certificates. All of that's going to be handled automatically. Just allow us 7 days for those to be processed, 7 business days, I should say, for those to be processed. And again, you're going to receive an email tomorrow, about 24 hours from right now, with more information about that. Jim, thanks for a great presentation. Thank all of you for attending. If you want to see our full webinar schedule, you can go to metalarchitecture.com/webinars. Thank you all. Appreciate it.
Take care.
Thanks, Jim.